Okay, well, welcome everyone. My name is Daphné Lemasquerier. I'm a research fellow at the University of St. Andrews, and I'm also an early career board member for Physical Review Fluids. So I'm very happy to moderate this journal club. So we have these, for those of you who are not familiar, we have these journal club events roughly every month where we try to highlight a paper very recently published in PRF. So just a quick reminder about the format before we start. There will be a 15-minute presentation. During the presentation, please stay muted. It's a short presentation. You can send some questions or comments in the chat during the presentation. Otherwise, just wait for the Q&A after the presentation to ask questions. And the Q&A will last 15 minutes as well. So the guest speaker for this journal club is Valentin Dorel, who is going to talk about a paper published in May in PRF about laboratory modeling of moist convection using a reactive fluid. So Valentin Dorel was a PhD student at Aix-Marseille Université at IRFE Laboratory. And this work was done in collaboration with Michael Lebars, also at Aix-Marseille University, and Daniel Lecoanet, who is at Northwestern University. So please, Valentin, go ahead, present us this very nice work, and we look forward to the discussion with you.
Thanks a lot, Daphne. Thank you everyone for inviting me at this journal club. So I'm Valentin Dorel, and I present you this paper we published with Michael and Daniel about moist convection and an experiment we made. All right. So to start, what is moist convection? So convection is the motion of fluid due to a difference in density. And the most studied case of convection is Rayleigh-Bénard convection, which is pictured on the right. So basically, you take a fluid of height h and you place it between two plates. The bottom one is hotter, and upper one is colder. There's a temperature contrast delta T between the two plates. And if this temperature contrast is high enough, the fluid starts to get in motion, it's convection. But Rayleigh-Bénard has been very studied, but it's in fact very far from atmospheric convection. And moist convection is part of atmospheric convection. It happens in the troposphere, which is the lower part of the atmosphere, so between 0 and 10 kilometers. And moist convection leads to the formation of clouds. So the base mechanism of moist convection is the fact that the heating comes from the condensation of water droplets. So water vapor condensating as form of droplets and releasing latent heat, heating the air around. A second phenomenon is the fact that saturation humidity, the humidity at which air becomes saturated, generally decreases with height. So basically, you have warm and moist air at the level of the ground. It rises because it is warm. And as it rises, it's become easier and easier to saturate because saturation humidity decreases. At some point, it becomes saturated, so it starts to condensate. So droplets are forming, and the air is becoming hotter because of the latent heat released. So it continues to rise and maybe condensate even more. So the heating in this cloud, which is starting to form, is internal, because everywhere in the clouds, you have droplets condensating. On the contrary, in Rayleigh-Bénard, the heating is only on surface. The heating here is associated to a threshold, which is the saturation humidity. If the air is not saturated, you have no heating, and as it becomes saturated, you have heating. And finally, you have a competition between buoyancy, which wants to make this runaway effect of condensating, releasing latent heat, making the air rise, condensating even more because the saturation humidity has decreased, rising again, and so on. And mixing, because as the cloud rises, it generally mixes with the ambient dry air and loses some of its humidity. If you want to study moist convection, for example, do a perfect model of a cloud, it's practically impossible to do a DNS because you would need to model the scale of the droplet, which is about a micrometer, and the scale of a cloud, which can be several kilometers. In terms of time scale, it's the same. It goes from milliseconds to hours. So you can do a direct numerical simulation of a cloud. You need to take some approximation. So there are several ways. You can still do a numerical model, but then you need subscale parametrization. You won't resolve the small scales. You can also do local models. So just look at some part of a cloud, for example, what happens at the top of the cloud and quantify the mixing there. So you can do it theoretically, or you can also do experiments, as Shai and Valentin did. Or you can do a simplified model, so take big assumption, which simplifies the problem a lot, and then it becomes accessible to DNS. That's what made Valis in 2019 with the Rainey-Bernard model. And in the same spirit, you can make an experiment which reproduces just some key aspects of moist convection. And that's what we did. So the starting point for our experiment is, as I mentioned, the Rainey-Bernard model from Valis in 2019, and two experimental studies, one from Krishnamurti in 1996, and one from Taylor and Bredenthal in 1998. Basically, our experimental setup is the one of Krishnamurti. So the 3 points we want to reproduce in our experiment are the internal heating associated to a threshold and the competition between buoyancy and mixing. So our experimental setup is the following. So we have this tank of water, the lower one, which is initially stably stratified in temperature. In the water, we dissolved homogeneously a color indicator, which is BTB for bromothymol blue. This color indicator makes the water yellow and transparent when the water is acidic, so pH below 7, and makes it blue and opaque when the water is basic, so pH above 7. Initially, the whole water is a bit acidic, so pH around 5, so everything is yellow and transparent. At the top of the setup, we put a big sodium lamp, which emits orange radiations, which are not absorbed by the yellow and transparent water. And finally, at the bottom, we put a copper plate, and at the top, we put a stainless steel wire grid, and we link the two to a DC power supply. And when the power supply is turned on, the electrolysis of water happens. At the top, we create H+, so it's becoming more and more acidic. It stays yellow. And at the bottom, we create HO-, so it becomes more and more basic, and at some point, it turns blue. So the blue layer initially grows upwards by diffusion, and this layer is absorbing the incoming orange light. So the absorption of light is ruled by Beer-Lambert's law. So the heating in the blue layer is internal. The pH in our experiment is the analog of moisture in the atmosphere, and we recover a threshold because if pH is below 7, the water is yellow and transparent, we do not heat. If pH is above 7, we are basic, blue, and we heat. And finally, as the blue fluid rises, it mixes with the yellow ambient and base reacts with acid. So we recover competition between buoyancy and mixing. Let's see what experiments look like. So these are two pictures from two experiments. And one easy parameter to vary is the total concentration of BTB we initially dissolve in the fluid. So when we change the concentration of bromothymol blue, two things happen. We change the penetration depth, delta, which is the typical depth over which the light is absorbed in the blue layer. And as we rise the concentration of BTB, this penetration depth decreases. And the second effect is when we rise the concentration of BTB, we rise the heating, the amount of heat. So this experiment is with a high concentration of BTB, and this one with a 10 times lower. So let's see what happens in the movie. So all the motions in the lab are really slow. So this movie has been accelerated 240 times. So the tank is 20 centimeters high, and initially all the water is yellow and transparent. Then we turn on the DC power supply. We see the blue appearing at the bottom, going initially by diffusion, then absorbing the light and starting to rise in the yellow ambient. We see instabilities developing at the interface between the yellow and blue layer and small plumes of blue rising in the ambient yellow. You can see that some of these plumes are disappearing because base has been neutralized by acid. Finally, you can guess that it's very hard to make quantitative measurements in this experiment. The lamp is too bright, so you can't make PIV, and the 3D, the fact that it is 3D makes that plume can superimpose on each other. So this was for a high concentration of BTB. Let's see what happens when it's 10 times lower. So same thing, initially everything is yellow. And this movie has been accelerated twice as the previous one, so 480 times. So we see the blue appearing at the bottom and the blue layer starting to grow in the ambient yellow. It's a bit slower than in the previous movie, and it should be twice faster. So everything is much slower in this experiment. And we still recover an instability between the blue and the yellow layer, and we still see plumes of blue rising, but these plumes are way bigger than in the previous movie. So to do a small recap, when we increased the BTB concentration, we heated more in a thinner layer, and we saw that the instability develops faster and the wavelength of the instability is smaller. And we wanted to recover this trend thanks to linear stability analysis. So first we did a full nonlinear model and then we linearized it. So we'll notify the irradiance, the light flux, little c the BTB blue form concentration, the concentration of the absorbing species, and big C the HO minus concentration. So first equation is Navier-Stokes with no surprise. Second equation is the heat equation with just an internal heating term, which is quite logical because you heat when you are blue and you have light. So you need both C and phi to heat. This equation is Beer-Lambert equation. Then we have our advection diffusion reaction equation on HO minus concentration. For linear stability analysis, we suppose that the chemical reaction didn't play a role and we neglected this term. This last equation comes from the pKa of BTB and just relates the concentration in blue and the concentration in HO minus. Basically, it's pictured here. And what it means is very simple. When big C is below 10 to the minus 7, pH is below 7, the water is acidic, so there's no blue, little c goes to 0. And when pH is above 10 to the minus 7, pH is basic, the whole BTB is blue, so little c goes to Ct. So to do our linear stability analysis, we made a quasi-static approach. So we didn't suppose we were at diffusive equilibrium because it's not the case in the experiment. So we computed base profiles depending on time. Then we froze this profile and added small perturbations. Then we need to validate the decoupling between the growth of the perturbations and the evolution of the base profiles. And we want to recover the two things observed experimentally, so the variation of growth rates and wavelengths of the instability with the BTB concentration. We can look at the linearized non-dimensional equation. So we use the classical heat diffusivity scales for non-dimensionalization. So we recover the classical Rayleigh and Prandtl number characteristic of thermal convection. Just note here that delta T is stabilizing in our case. We have this dimensionless parameter coming from the pKa of BTB, the Lewis number, comparing diffusion of heat and of HO minus, and two dimensionless parameter characteristic of our setup, beta, which is the dimensionless absorption depth, and Q representing the heating. We recover the fact that when we change the BTB concentration, we change both the concentration depth and the amount of heat. So we have this equation for the base profiles, and we can also look at the equation for the perturbations. So we note theta the perturbation in temperature and V the perturbation in velocity, and we'll just look at the terms which are responsible for our instability. So our instability is convective, so it has to come from buoyancy. This perturbation in temperature theta will come from the perturbation in blue concentration, little cp, and this perturbation in blue concentration will come from the advection of the base HO minus profile. We'll just see that now in the mechanism we propose for our instability. So we take a point at the interface between the lower blue layer and the upper yellow one. We take a Eulerian approach, so this point is fixed, and we suppose that we have a positive small temperature perturbation at this point. So because there's a positive temperature perturbation, it induces an upward small velocity at this point. So downward fluid will be advected through this point. The lower fluid is more basic, hence it will become more basic here, hence bluer. And because it's bluer, it will heat more, so the perturbation in temperature will grow, then the velocity will grow, and so on. So we have an instability where the base mechanism is the advection of the source of heat. Now we can do our linear stability analysis using Daedalus. We decompose our problem on Chebyshev in the vertical direction and on Fourier mode of wave number m in the horizontal one. At each time, we solve the problem and look for the most unstable mode. And we vary the BTB concentration, hence Q and beta. And we obtain graphs like that. So it's growth rate sigma versus wave number m for several times t at which we computed the base profiles. This is for high BTB concentration. Remember, we need to validate our quasi-static approach. We need to validate the fact that the instabilities are growing much faster than the base profile's evolution. So the typical timescale of evolution of the instability is 1/sigma. The typical timescale of evolution of the base profile is t. So we take sigma times t greater than 10 for our criterion. So on this graph, crosses indicate that this criterion has not been met. So this approach is not valid. And dots indicates that this the criterion is met. So to tell what mode predicts is predicted thanks to this linear stability analysis, we take the first curve on which we see dots, and we take the maximum of this curve. So in this case, it tells us that the instability should have a wavelength, a wave number m equals 14, which is quite coherent with what we observe experimentally. Last thing we can see on this graph is that growth rates are around 6,000 to 8,000. And when we take the same thing for 10 times lower concentration, we see that growth rates are way smaller. We recover the fact that when the concentration is lower, everything goes slower. And we do the same on this graph. We take the first curve for which we have dots, and it predicts that the most unstable mode should have a wave number m equals 8. So we recover the fact that the wavelength is greater when the concentration is in BTB is smaller. We recover what we saw experimentally. So to conclude, we made an experimental setup reproducing key ingredients of moist convection. We saw a convective instability whose growth rate and wave number varied with the concentration of BTB, and we recovered this variation with linear stability analysis. The next step to do using our experimental setup would be to study the nonlinear dynamics. Thank you for your attention. I'd be pleased to have a discussion.
Thank you very much, Valentin. So if anyone has questions, please raise your virtual hand, or if you prefer, you can put your question in the chat, whichever is fine. I can start with a quick question just to let people time to think about what they want to ask. I just wanted to ask you, Valentin, how does your model compares? I didn't have the time to follow everything. I was wondering how it compares to the Ramey-Bénard model of moist convection. Are there fundamental differences, and if yes, what are they?
Yeah, basically, there's differences. In fact, in the Ramey-Bénard model, they include compressibility effects that, of course, do not play a role in our experiment. And the second main difference is the Beer-Lambert effect, which is present in our setup and not present in their model. So the fact that the upper part of the blue layer is more heated than the lower part. So that's why experiments with low BTB concentration experiments where the heating is more homogeneous and should be the one closer to a cloud or Ramey-Bénard model.
Okay, I see. Thank you. I see that Lucas Klotz have their hand up if you want to ask your question.
Yes, I have a question. You said that the exposure is too bright to use the PIV, but have you considered using the filter for the light? I mean, just to filter out any light that would be different than the laser light? Maybe as this you can get some ideas about the PIV field.
Yeah, we tried to put, for example, a green laser because it's not too much absorbed in the yellow or in the blue, and then to put a filter just at the wavelength of the laser. And even with that, the lamp is really too bright. And the only option we considered, but we did not apply it, would be like because everything is slow, you can take maybe one frame every 10 or 20 seconds for PIV. You should be to have a motor which just put a plate under the lamp to hide the lamp light. Then you take your frame and then you remove the plate. It shouldn't affect too much the dynamics because it's really fast compared to the time scale of a flow, and it should be possible to do PIV this way.
Okay, thanks.
Nadir?
Hi, Valentin.
Hi.
This is Nadir Jeevanji from GFDL in Princeton, New Jersey. It's great to see this work as someone who's thought about Mohs convection for a long time. Really nice to see an analog in the laboratory. I really like this movie that you have playing here at the end. I guess this is the low BTB scenario.
Yeah.
And so I've run a lot of simulations of moist convection that are kind of more on the realistic side, and this case sort of like looks more realistic to me in some ways, and I'm sort of asking myself why do I feel that way? I think part of it is that I'm getting some sense of organization, that the plumes maybe want to clump together, and that I also see one plume following another plume. This is an idea that's sort of cropped up in the moist convection literature, sometimes under the name of thermal chain. Some papers from Huey Morrison that you may be familiar with. Is that your impression too? And do you think that there's these qualitative differences that I was just talking about? Do you think those really exist between this regime and the higher BTB regime in terms of more organization and thermals following each other?
Yeah. So we had the same impression as you, Nadir. So yeah, in the high BTB case, we did not see as much clustering as in this case. So it showed the same things that our intuition, that this case should be the one closer to moist convection, because the heating is more homogeneous, whereas in the high BTB case, there's a huge discrepancy between the upper part of the blue layer and the lower part. And we actually did also DNS of our setup. And when we see the DNS, I can play you a movie from the parameter of this experiment with low BTB concentration. And we recover a form of clustering of initial plumes to bigger structures.
Cool. Very nice. Thank you.
No problem.
We still have time for a couple more questions or comments, if anyone wants to step in. Trying to browse. I think I would see raised hands. I was wondering, I'm gonna ask a question if no one wants to. In your paper, I seem to recall that you were mentioning some issues with gas bubbles forming at one electrode. Which one was it? Was it at the bottom, and then they would rise? Both.
Yeah,
okay.
both, but on the upper one, it's not really a problem because the rising does not affect the flow. But yeah, in fact, the electrolysis of water, as you may know, creates H2 and O2. So H2 is created at the bottom electrode. And so we were limited in the electrolysis current we used, because when this current was too high, we only saw bubbles rising. I can maybe show you the movie. If I just played the first movie I showed you longer, we would see the bubbles effect. If we go there, you can see this very fast events appearing. They should be appearing more and more. For example, these are big bubbles just popping off the lower plate and perturbing the flow. So we had to lower the electrolysis current. Then we did not see these events which are appearing more and more, as you can see.
Yeah, I see. I was wondering if the time scale could help you, because presumably they rise much faster than the convection time scale, but they seem like huge bubbles. So even if they rise slowly.
Small bubbles, there's probably small bubbles rising before, and maybe there's not a problem. Sometimes we see like traces of just a point where all bubbles are rising of a form of a thin blue column. But these big bubbles are really a problem. But when we lowered the electrolysis current, they did not appear anymore.
Okay. Do we have other questions in the audience?
I can ask another one.
Yeah, please go ahead.
So one thing we think about in atmospheric science context is the effect of variations in the environment, say the environmental relative humidity on convection. So even for quote unquote the same amount of mixing, if the environment is drier, it has more of an impact on the convection. Is there an analog here, and are you able to probe it?
It's interesting, yeah. Yeah, you can what you can do here maybe is change the initial pH. So if the initial pH is 5, so it's just a little bit acidic. If you make the initial pH like to be 4, so it's 10 times more acidic, and so the blue plumes will be much more, won't rise as much because the base will be neutralized way faster. And so it can be an analog of a drier environment because it will, base will be, yeah. And in fact, we did experiment, and so we can't go at too high acid concentration, otherwise there's other chemical instabilities appearing, but we can reach like pH 4, and this will change the dynamics, but we did not do a whole systematics on pH yet.
Gotcha. Cool. Thank you.
Thanks, Nadia.
I can ask maybe one final question before we conclude. I just wanted to know, like a very broad question, what is your understanding of what are state-of-the-art parametrizations for these processes right now? What are the limitations for the parametrizations you mentioned at the beginning of your talk? And what do you think are the challenges in terms of how these parametrizations are currently done, and what we could do, from experimental results like this, what could bring?
Yeah, so it's quite difficult because many models use parametrization and do very well of predicting the weather or other things. So it's not because they use parametrization that everything they say is false. But if we want to make sure that we fully understand what we do, it's good to have a bit of comparison. And I think these experiments will help us to identify the key phenomenon and maybe the phenomenon that we are sure we can't parameterize. And if these phenomena are suppressed, then the dynamics will be completely false. And experiment like that maybe can, and simplified model as Rainy Bernard, help us to, because there's no parameterization, identify maybe a key phenomenon. I don't know if I answered really the question, but.
Yeah. I was wondering, do you think, I guess are we in the good regimes, like with these experiments, in terms of like the regimes
of course, in terms of Reynolds number, we are not, because all the movies were accelerated, as I told you. So Reynolds is close to 1, in clouds is close to 1 million, so 10 to the 6, so it's a little difference. But it's not because we have 6 order of magnitude that our experiment is not relevant at all. There has been previous studies of laboratory analog of what happens in the atmosphere, where as in our experiment, the Reynolds number was 5 order of magnitude lower, and they found similar entrainment rates as in the atmosphere. So, of course, it's a problem, but it's not completely, it does not mean that it is not relevant at all.
Okay. Thank you very much.
Thanks, Daphne.
I think there's Lucas.
Yes, I have one last question, if I may. How linear your system is when compared to the classical Navier-Stokes equation? And what is the nature of nonlinearity in your system?
So, yeah, so this is our full model. So Another source of nonlinearity is this internal heating term, because it make there's both the blue concentration and the irradiance which appears, so it's another nonlinear term. And of course, this very nonlinear relation between the blue concentration and the H-minus concentration, which represents the threshold, which is a big source of nonlinearity in the moist convection processes.
But your system is somehow more nonlinear than the classical Navier-Stokes equation, or it's comparable, like in the terms of amplitude of nonlinear terms when compared to the linear ones?
I think there's like this threshold term is a very high source of nonlinearity and makes the system really more nonlinear than just classical Navier-Stokes, because it's as we can see here, it's on log-log scale, but the transition is really, really sharp, and it's a really high source of nonlinearities.
But your linear modes are still relevant, right?
Yeah, and we show that it's relevant at the start, because when we do DNS, we see the linear stage of the instability before nonlinearities kicks in.
Okay,
so
perfect.
there's a linear phase.
Thank you very much.
Okay, I think this brings us to the end of this journal club. Thank you again, Valentin, for a very nice work and very nice presentation.
Thanks, Daphne.
Yeah, we'll reconvene in September, I believe, for the next journal club. Thanks very much, everyone. Have a nice day or end of the day.
Thank you.
Thank you, everybody.